For those of you who don't know me, so I'm a research associate right now with National Institute of Standard and Technology, NIST, and also I'm a research affiliate with the University of Colorado Boulder and also University of Maryland College Park. Today I'm going to present a research on optimal seismic intensity measure selection for concrete dams. So I will mainly focus on the gravity dams, and I will explain a framework, a general framework, which leads us towards a generic PBE framework. So this research is, I did this research mainly when I was a PhD student a couple of years ago with Victor Salma from University of Colorado Boulder. And also part of this research, the recent ones, I completed in collaboration with Dr. Sanas Rezaian from USGS, Colorado also. So let's start with some backgrounds. The potential failure mode analysis, or PFMA, still is a state of the art in dams, at least in the United States, as long as I know, and it mainly refers to a chain of events leading to unsatisfactory performance of dams and finally uncontrolled release of the water. So that the procedure can be, the initial part of the procedure is mainly qualitative. So there are some quantitative aspects that we can add at different levels and finally lead this entire effort towards the decision making. However, the approach, which is the state of the art in the buildings and bridge industry, so is PBEE, or the next generation of PBE, or performance-based earthquake engineering, which tries to separate four main aspects of hazard analysis, structural analysis, as you can see in the second figure, damage analysis, and loss analysis. So these four main parts are integrated to each other through this main framework, which we call the second generation, or PBE framework, or the one that generated with the Peer Center at the University of California, Berkeley. And the first one, which is the hazard analysis, I think a couple of our previous presentations today was mainly focused on this one, how we can perform a probabilistic seismic hazard analysis, how we can select the ground motion, how we can scale the ground motion. Even Pierre mentioned that how we can have, a synthetic ground motions to be used for the analysis. So the second part is the structural analysis, which uses directly the results of ground motion selection and scaling for the finite element analysis. So this was part of the Benjamin's presentation. So the third and fourth parts are mainly referred to the damage analysis in the context of the fragility models, and the loss analysis that incorporate the factors such as monetary loss, the loss of life and downtime. And it is mainly important for the stakeholders, for the managers that help them for the final decision making. So what we are trying to do is to combine and integrate these two, because there are some elements in the PFMA that we cannot see definitely in the PBE, which is mainly developed for the buildings. However, in generic, the PBE is a very comprehensive framework by itself. And also back to the current framework and gap identification. So the majority of the research that if I track for the papers which are published in the past 2 decades, at least in the field of the concrete dam engineering. So you can see that many papers focus on dam foundation interaction and wave propagation. So the dam fluid dam interaction or reservoir dam interaction, how we can handle the pore water pressure inside the open joints, and also how we can incorporate the nonlinear analysis in terms of either the continuum mechanics, or the discrete crack models. So this was the majority of the focus recently in the past 2 decades on the in the field of the dam engineering. And back to the topic of the earthquake engineering related to the dams. So we can definitely consider the pre-earthquake domain, the earthquake domain, and the post-earthquake domain. So in the pre-earthquake domain, we mainly developed the initial finite element model, sometimes simplified. So because we are not dealing with high nonlinearities, so we need to apply the interactions like, again, the soil structure interaction, fluid structure interaction, the aging models such as AAR, as you heard before in this series of presentation, the thermal analysis, all these things are usually applied in the pre-earthquake domain. So, and it may take like from a couple of weeks to years and decades, this pre-earthquake domain. So the earthquake domain, so in this domain, which takes usually seconds to minutes, so you need to really modify your finite element model. Usually you need to finer mesh. So you need to modify the input parameters. If you are using the material properties, you need to consider dynamic properties for your analysis. And in the post-earthquake, you also need to, again, apply another layer of the modification of the finite element model to somehow consider the pre-existing damage in your model, including the critical response and also the post-seismic risk analysis. So this is the current again framework, and I am trying to put more weight on this part to identify the current gap, because this leads us, if we understand the importance of the problem, so we can perform very effective research in future. So again, back to the application of the PBE in the dam engineering. So I can say that it is very limited. So the state of practice in dam engineering, as you heard from the couple of previous researches, deterministic evaluation, usually we try to do the best finite element model analysis that we can do. So there is no official guideline on the application of the probabilistic techniques. So many people usually adopt and change a little bit whatever, you know, initially or previously presented in the nuclear engineering, building engineering, or bridge engineering. And also the current focus of the Dam Society is mainly on the best practice. So as we did with Jerzy Solomon and some other friends, so in the USSD workshops, through the ICOLD workshop, so we try to find if we have one single problem for different engineers or scientists, what is the variation or uncertainty of the results. And so the final finding was that in some cases the results are very close, and still in some cases there are very huge gap in doing just one deterministic analysis, especially in the nonlinear case. So understanding the current gap, so it leads us to the point that we need an urgent move in the research on a grand motion selection and scaling, both in the real and synthetic versions, and also the optimal seismic intensity measure selection for different type of the dams. So what I'm going to present today is simply all summarized in this page. So what we have is the hazard analysis. Let's say you have a scenario, or you perform a probabilistic seismic hazard analysis to find your dominant scenario, and based on that one, you either select the real grand motions from the database that you have, and in most cases it is not perfect because we are short in the number of the the grand motions which are appropriate for our scenario, or you synthetically generate your grand motions based on whatever software you have. So once you have all these, let's say, n grand motions, you fit it into your finite element code, because what I am presenting today is purely numerical. So you perform a CLAD analysis and you extract engineering demand parameters, which is a dam response, essentially, like the crest displacement or the amount of the joint opening, sliding, damage index in the concrete dams. So whatever it is, so for all these n grand motions or n simulations that you perform, you develop this matrix of engineering demand parameters. So at the same time, having these grand motions that you applied to the system, so you can perform some post-processing on those kind of independently from the finite element analysis, and you extract different intensity measure parameters. So for each grand motions, there are many intensity measures. I'm going to explain it later. And the combination of these two metrics, the metrics of input parameters and the metrics of outputs, so usually present in a form of the fragility functions or CLAD response, that we can use it to identify actually the optimal grand motion intensity measure for a concrete dam. So let's go step by step. For the case study, I use a very simple dam. So it's just a 2D concrete dam, a pine flat dam. I implemented a zero thickness interface, which is a discrete crack type, elements at the dam foundation interface. We are modeling the hydrostatic, hydrodynamic, and also the uplift pressure, which is dynamically updated with the applied grand motion and based on the amount of the joint opening that you have. We modeled the foundation, we modeled the convolution, we applied the recorded free field grand motion with the convoluted and applied at the base of the foundation. You see the boundary conditions that we use, of course, and as you heard from the previous presentations, this model that I explained right here, so it is one of the simplest models that one can use. There are very advanced models for the dam foundation and wave propagations, such as perfectly matching layers or some other methods, or we can consider the non-uniform grand motion for this one, but we neglect all these effects, or even you can consider the near fault far field effect. So all these effects are currently ignored in this research. And we use the in-house finite element called Merlin, which our team was working on it for about past 20 years. So back to the analysis type. So we are doing a probabilistic analysis. So once you are doing a probabilistic analysis, again based on the PBE framework, you have different choices. So you have the choice to do the CLAD analysis, the so-called incremental dynamic analysis, the so-called multiple strip analysis, on the endurance time analysis. I think we will have a couple of these methods reviewed later again today. So I choose to use the CLAD analysis. And what is the CLAD analysis? The CLAD analysis is a numerical procedure in which the structure, in our case, the concrete dam, is subjected to a set of unscaled grand motions. So the advantages of this method, the CLAD analysis, is that I do not manipulate the grand motion record in any way. So in other methods, such as the incremental dynamic analysis, you need to scale the grand motion up to the failure of the structure. And many researchers, scientists still have problem with this method because they believe that it is unrealistic. So I choose to use the CLAD analysis because I'm going to directly extract the intensity measures out of it, and I didn't want to manipulate in any way those records before extracting their intensity measures. So for this purpose, so let's say you have like 100 grand motions. So you apply those 100 grand motions one at a time to your finite element model, and you extract the outputs, let's say in this case, the crest displacement, and you pull out the intensity measures. The most intuitive one is PGA, and of course not the perfect one, versus the displacement. So the pattern that you see out of this is similar to cloud. This is why we call it cloud analysis. And in the arithmetic scale, it has a power 4, okay? So this is why if you transfer it to the logarithmic scale, you will see more or less a linear trend. Of course, depends on the choice of the IM parameter. So if you choose optimal IM, this will be more linear, as I will explain later. And the combination of, and using this this logarithmic scale, you can extract the slope, and also you can find the dispersion, and you can develop the fragility functions that is not, you know, the concept of today, and I'm going to escape it. However, back to the concept of optimal intensity measure parameter. So usually if you search the literature, especially in the field of structural engineering, so there are 5 metrics that leads you to optimal IM parameters. So a combination of these 5 metrics, so leads you to a optimal IM. So the first one is the efficiency. So efficiency is indicator of engineering demand parameter variability for a given IM level, okay? So let's say these dots here are the nonlinear transient analysis. So each dot represents a nonlinear analysis with this IM value and this EDP value. So if you find a beta value, beta of EDP condition on IM, and beta is also used in this fragility model in here. So it can be a representative of efficiency. So the lower the beta is, the higher the efficiency is that IM parameter. And it makes sense because if you look at this bell-shaped curve, if you have a lower beta, it means that the lower and upper bounds of these 2 dashed lines are more close to the solid line, and you have less variability. The other parameter or metric is the practicality. So it's indicator of the correlation between IM and EDP. Okay, higher the beta is, and beta is the slope of this line, as I mentioned in the logarithmic version, so represents the higher practicality. So definitely by higher beta, I do not mean 90 degree, because in that case it is meaningless. Usually the slope of this line is very small. It's like, let's say 5 degrees or 10 degrees. And if it moves to a 45 degree, so it means that the IM and EDP are in good correlation with respect to each other. So the third one is the proficiency. Proficiency is nothing new. However, it's a composite metric of the beta over B. And again, comparing the criteria that we had for those 2, we can say that the lower Z corresponds to higher proficiency. The fourth one is the hazard compatibility. So the hazard compatibility means that how easy is this IM candidate is to use. For example, you can find a IM which you require a very, very complex mathematical formulations to develop it. However, the hazard map, the seismic hazard map that you use to develop it is very difficult. And the final one is the sufficiency. So the sufficiency means that this selected IM, how independent it is from the other seismic hazard parameters such as moment magnitude, site to source distance or other things. So the higher p-value corresponds to sufficient IM. So what we did, we identified over 70 different IM parameters, and we categorized them in 7 different classes. The unscaled IM such as M and R, the grand motion dependent ones such as PGA, the compound ones such as, combination of PGA, PGV, other parameters, structure independent one such as acceleration, spectrum intensity, structure dependent spectral IM such as SAT1, and T1 is the first mode of your dam, the vector-based one, and the multiple component one, because we have three component grand motion eventually. So we applied, as I mentioned, a total of 100 grand motions on a dam. We used unscaled grand motion selection to select these grand motion records. We fitted different parameters, different, distributional models to all those IMs. So I'm skipping these parts very quickly. So what I'm going to show in this slide is that let's compare just spectral acceleration at the first mode, second mode, up to fifth mode with those that incorporate combination of first and second, first to 4, first to 6. As you can see, there's a large dispersion in here when you consider a single mode of the dam as the intensity measure parameter. However, if you incorporate the higher modes, again, this is somehow correlated to what Benjamin reported in his last slide. If you incorporate the higher modes effect and you consider the higher modes effect, you will come up with some intensity measures which are more optimal. So, and in this slide, I'm comparing, the practicality, efficiency, and sufficiency. So again, you can see the different intensity measures, and for each one, different EDP parameters. So the final conclusion from all this was that the spectral acceleration at the first mode and also spectral velocity are among the 2 optimal intensity measure parameters. However, the SAT1 is also hazard compatible because we have the hazard maps for those, and that one is highly recommended for the concrete gravity dams.